Today we are going to look at indeterminate forms and L'Hopital's rule. L'Hopital's rule will make taking limits a lot easier. So L'Hopital's rule actually wasn't discovered by L'Hopital. It was discovered by John Bernoulli, but Bernoulli worked as a math contractor for L'Hopital, and the understanding was L'Hopital would pay a stipend. John Bernoulli would just work on mathematics, but if anything he discovered, L'Hopital got to claim it. So L'Hopital was actually known for coming out with one of the first calculus textbooks, but L'Hopital's rule was discovered by John Bernoulli, but it will, as you'll see, will make life much easier for us. So these first three examples here are problems that we saw earlier this semester. And we had these indeterminate forms, and again, the software, for whatever reason, it looks a little weird when I upload it into this program, but this handout, section 4.4, is on Blackboard, and if you print it out, it will look more normal. It won't have this up here, and this won't be blurry. But we saw this example. This was in chapter 2, and it was type 0 over 0, which means basically if you take the limit right now, we plug in a 2 and we have x squared plus x minus 6 over x minus 2, we get 0 over 0. So this is one where we had this indeterminate form, and what we did is we learned that we could rewrite this. And because this one actually factors, we factored the numerator as x minus 2, x plus 3. The denominator was x minus 2. And then we saw, well, we could actually cancel these. As long as we're taking the limit, we can do that. And we get x minus, the limit as x approaches 2 of x plus 3, so we get 5. So if this problem would have been a little bit different so that this wouldn't factor and this wouldn't cancel, then if we had 0 over 0, we would just not be able to do that problem yet. So all of the problems that we had were factorable. Then we had this other infinity over infinity, and this type, if we look at this one, and we have the limit as x approaches infinity, the numerator is going to go to infinity, the denominator is going to go to negative infinity. And this was a type where we had a technique that said just basically multiply, or actually divide by everything by the highest power in the denominator, which we showed it by doing this, by multiplying by 1 in this form, which is essentially multiplying everything by the highest power in the denominator. And then we'd say, so this is the limit as x approaches infinity, and we would get, so we'd have x squared over x plus x over x. On the bottom, we'd have 3 over x minus x over x. So when you clean that up, we have the limit as x approaches infinity, x plus 1 and 3 over x. Oops, minus 1, actually. It's going to be a minus 1. So we end up with infinity over negative 1 or negative infinity. Then this last one, we used a geometric proof, and this one took a while to do, but we used a geometric proof to show this was equal to 1. I'm not going to repeat that proof here, but we did that earlier in the year. So we're going to actually have a way, and this was actually a 0 over 0 type of problem. But we're going to have a way to do these much easier than any of those three methods right here. So before we do it, we have to talk a little bit about indeterminate forms, and we've seen some of these, but we're going to actually see all of them right here. So limits are said to be indeterminate form when knowing only the limiting behavior of the individual parts of the expression is not sufficient to actually determine the overall limit. And there are 7 of these indeterminate forms that involve zeros, ones, and infinities. And these are the 7. And we've seen 0 over 0 a lot. We've seen infinity over infinity. And we've seen some of these other ones. And now we're going to see these power indeterminate forms. But just to make note of something, not every combination of these are indeterminate forms. So here are some that are not indeterminate. So as an example, infinity plus infinity, you can't add 2 limits that are approaching infinity and get 7, for instance, right? Infinity plus infinity, that's just infinity. Infinity times infinity, that's just infinity. Things like 0 over infinity, that's 0. Infinity over 0, that's infinity. So it isn't just any combination of these that work, but these are indeterminate. These could be absolutely anything at all. Because remember, these are not numbers. This is not actually the number 1. This is a limit approaching the number 1, while at the same time it's being raised to a number approaching infinity. So these are all like races. It's a race between this numerator going towards 0 and the denominator going towards 0. So this is just saying these things are not numbers. They are descriptions of function behavior. So it's like it's a struggle between these 2 quantities to see which one is getting where it's going faster. So we've got some examples of indeterminate forms, and of course we have this weird big gap here on this page. And okay, this is really this is really kind of a messed up page here. So again, the handout that you have, if you download it from Blackboard, doesn't look so weird. But we've got some examples. So right here we've got indeterminate form 1 to infinity, and this is a famous one. If you look at this, as x goes towards infinity, this base here is going towards 1 because this x is getting bigger and bigger. So this term is going towards 0, so you have 1 plus 0. But at the same time, the power is going towards infinity. This is a very famous one. Some of you will recognize it, but the limit of this is e. The famous number 2.71828, and it just keeps on repeating, or keeps on not repeating, keeps on going forever. Here is another example of 1 to the infinity. Another one that's 1 to the infinity. This one goes to infinity. And then there's another example of 1 to infinity, and this goes to 0. So we've got 3 different examples of 1 to infinity, and we get 3 different answers. So then we've got some infinity over infinity, a couple of them here. Now some of these you can see what's going to happen. Without even going through the usual routine where we would divide by the highest power in the denominator, which would work, but you can sort of see what's going to happen. This denominator is going to dominate the numerator because this is an x squared. So in this case, this one, because it will dominate this one, this can be as far away from this as we want to. This denominator could completely dwarf the numerator, so this thing is going to just go towards 0. And that's one we would have been able to do before, just using the technique that we did before, which is kind of the go-to technique for infinity over infinity. Now in this case, if you do that technique, because these powers are the same, this term will dominate the numerator, this term dominates the denominator, so long term this thing is going to act like, as this gets really big, it's going to act kind of like 2x cubed over 2x cubed, which is just 2 over 2, or 1. So it's just showing, again, you can get different answers for these indeterminate forms. And here are some more. Actually, all of these are the form infinity over infinity. And just looking at the powers, we can see this is another one. These powers are the same, so the lead coefficients being 2 and 3 means this will the limiting value of this expression is 2/3. Over here, the numerator will dominate because this is an x cubed over an x squared. This will totally dominate. And so that one is going to be unbounded, so the limit we would say is infinity. Over here, looking at e, again, these powers are the same. So the limit of this is going to be -5/8. And then finally, the last one, we've got an x squared here, which should dominate, but there's a negative here. It will dominate this denominator, which is 2x, so we will end up with -infinity. So this is just showing that for this infinity over infinity, you've got this one indeterminate form here. All of these are this indeterminate form, and you can see there are a lot of different answers for that. So any of these indeterminate forms could literally be anything at all. And that's why we have to evaluate each of them independently. Well, L'Hopital's rule, what it does is it uses derivatives to help evaluate limits involving these indeterminate forms, and it works on all 7 of those. So for L'Hopital's rule, suppose that f and g are differentiable functions, and g prime of x is not equal to 0 near a. Remember, we're dealing with limits, except possibly at a, which of course we, again, don't care what happens at a. And then the limit as x approaches a of f of x equals 0. Well, if the limit as x approaches a of f equals 0 and the limit of g of x as x approaches 0, so they both are 0, or both of these limits are some sort of infinity, then L'Hopital's rule says this. It says that the limit of f of x over g of x is exactly the same as the limit of f prime of x over g prime of x. So we individually take these derivatives. It's not the quotient rule. That's a really easy mistake to make, but it's just the individual limit, or the individual derivative, f of x, f prime of x, g of x, g prime of x. And L'Hopital's rule says that these will be the same. The limit of f of x over g of x is exactly the same as the limit of f prime of x over g prime of x. So, in other words, if we have either of these indeterminate forms, and this is the key, L'Hopital's rule requires this. So, one thing that's really important to understand is this. L'Hopital requires one of these forms. So remember, there's 7 indeterminate forms, 7 of them. For us to use L'Hopital's rule, we need one of these 2. And if that's the case, then this rule applies. And one thing to note is that it doesn't have to be x approaches a. It could be x approaches infinity, negative infinity, and even one-sided limits hold as x approaches a from the right or x approaches a from the left. So all of these hold. We just have to make sure that we have one of these 2. And we're going to see that no matter which of those 7 indeterminate forms we start from, we can turn them into one of these 2. There's a little picture on page 305 if you have the 8th edition, or page 302 on the 7th edition. It's in the margin. And I'm going to just talk about that picture. It basically shows why L'Hopital's rule seems reasonable, seems plausible. So let's say we have an XY plane here. And we've got this point A. And let's say we've got function f that goes like this, and maybe function g which goes like this. So here's f and here's g. So let's say we zoom in. We're going to zoom in at A. So we zoom in around here. Okay, so let's say we zoom in at x equals a. And you guys have done this plenty of times with the graphing calculator. Once you zoom in, then the graphs always seem to flatten out. Right, so if we were to zoom in here at a, so let's just say a is here, but we're zooming in here, and then we zoom in right at this point, and now it looks like f is flat, and it looks like g is flat because we're zooming in right there. So remember that this point here, this is the point a, 0. X is a, y is 0. And what we're going to do is we're going to use this formula from algebra class. Y minus y1 equals the slope times x minus x1. And let's just look at the equation of this line f. If we use this, y minus y1, which is 0, right? So we have, for f, we would get y equals, because y minus y1 is 0. The slope, we'll call the slope of line f slope 1 times x minus x sub 1, which would be a, right? Because this line f is going through this point a0, so we plug in a and 0, and we get this. So that's for f. And then for g, do the same kind of thing for g. We will get y minus y1. Again, it goes to the same point, so it's still going to be y minus 0 equals the slope 2 times x minus x1. Again, x minus a. So these lines, they look like they were linear. Now, we know they're really not. They're not linear, but when we zoom in, they look like they're linear. So when we get really close to a, these look like straight lines just because we know we're zooming in. So they seem to flatten because we're zooming. So they're not linear, but if they were linear, so if they were linear, then we would have this ratio. Let's say we've got this ratio, which would be the ratio of f to the ratio of g would look like this. If they really were linear, we could have this ratio of the two. And then, of course, this would cancel, and we would get m1 over m2. Well, m1 and m2, this is the ratio of their slopes. Ratio of the slopes, but really the slope is the geometric equivalent of a derivative, so it's really a ratio of their derivatives. So when we get really close to a, we zoom in around a, we get this flattening, so that if they really were linear, the ratio of the lines would be equal to the ratio of the derivatives, which suggests this. It suggests, it's definitely not a proof, of course, but it suggests that, let's say, suggesting that the limit as x approaches a of f of x over g of x, right, as we get really close to a, we zoom in here, we get really close to a, the limit of this f of x over g of x looks like it might be the limit as x approaches a of f prime of x over g prime of x. So again, it just seems plausible that would work. Some of you who are super lucky and will take calculus 5 will probably get a chance to prove L'Hopital's rule. But for now, we just have to be aware of it and know how to use it as Calc 1 students. So let's see how we use this. So we've got some examples here that we've just seen, and now we're going to use them the easy way. So here's what we can do. when you look at this first one, we say, okay, if I plug this in, I get 0 over 0. So we can use L'Hopital's rule because L'Hopital's rule needs one of these two forms, right? 0 over 0 or infinity over infinity, and we've got one of them. So what we can do is we say this equals, and to show you using L'Hopital's rule, typically what you do is you put a little h here. Put a little h here, and you say this is equal to the limit as x approaches 2. And now we take the derivative of these individually. The derivative of this first function, x squared plus x minus 6, the derivative of that is just 2x plus 1. So the limit of this other function, x minus 2, the derivative of that is just 1. And now we can take the limit with no problem. You plug in a 2, right? Plug in a 2 and you get 5 over 1, which is 5. So you can see that this would work even if this didn't factor. Remember before, we could solve this one because it factored and canceled with x minus 2. But we said that if it didn't factor and cancel, then we just couldn't do it before. But now we'll be able to do it pretty easily with L'Hopital's rule. So same with this other one. We look at this one and we say, okay, we've got infinity over negative infinity. That's one of the forms. Remember, it's either 0 over 0 or infinity over infinity, and the pluses and minuses don't matter. This form is ready to go for L'Hopital's rule, so we put our little h here so that if somebody is watching our work, they know what we're doing here. And the derivative of each of these, so the limit as x approaches infinity, and we're going to get 2x plus 1. And on the bottom, we get a negative 1. So as x goes to infinity, we're going to get infinity over negative 1 or negative infinity. So pretty easy with L'Hopital's rule. And this one is especially easy because if you remember before, when we look at this one, we had 0 over 0, and we did not have a good way to do this one. And we had to resort to a geometric proof that pretty much everybody uses for this. But now we've got a much easier way. It's 0 over 0, so we can just use L'Hopital's rule and say this is the limit as x approaches 0. The derivative of sine is cosine. The derivative of x is 1. And now we can take the limit. We plug in a 0. The cosine of 0 is 1, so we just get 1. And saved a good 15 minutes at least of doing that geometric proof. So got some more to look at here. So remember with this video, when I'm going to do example 4 here, but what you should do first is try it on your own like we would normally do in class, and then see what you get. The only differences on these videos, I won't be torturing you guys with my super funny jokes. So you have to insert one of those bad dad jokes every once in a while so it feels more like a class. But for this one, we've got a limit as x approaches 0. So if you plug in a 0, you get a 0 on the top. On the bottom, we're going to get 1 minus e to the 0, which is 1 minus 1. Which gives us 0 over 0, which is the one we need. 0 over 0 means we can go ahead and use L'Hopital's rule. So this is going to be the limit as x approaches 0 of 1. So the derivative of e to the x is just e to the x. We've got that negative out there, so it's negative e to the x. And now we take the limit, we plug in a 0, and we're going to get 1 in the top, and negative e to the 0, which is negative 1 on the bottom, so we get negative 1. So we've got another couple examples here. And this one gives us some trouble. So you might want to try this one on your own, and just to give you a warning, don't fall into a trap. Here's the hint. You can only use L'Hopital's rule if we have 0 over 0 or infinity over infinity. So try that one out. And maybe you're back now, so we can look at this one. And again, hopefully you're trying these out on your own so you can, run into some of the little problems that we all run into when you first see these. So once you plug in 1, I plug in 1 in the top, and I get a 4. So I'm not getting it like 0 over 0. So I get a 4 on top, plug in 1 in the bottom, you get negative 1. So it's just negative 4. So you don't need L'Hopital's rule. So I'm going to put a little caution here. So don't use L'Hopital's rule every time. Now the problem is this. If you use L'Hopital's rule, everything seems fine. You're just going to get a wrong answer, but you might not know it. So if you use L'Hopital's rule, you would do something like this. You'd say, got the limit as x approaches 1 of 3x plus 1 over x squared minus 2. I'm going to go like this and take the limit. X approaches 1, you get 3 over 2x, then you get 3 over 2. The problem is it's all wrong. This whole thing is wrong. We can't use L'Hopital's rule here because we don't have indeterminate form, so we always have to check. We check and see if we can use L'Hopital's rule. And here we can. This one's just ready to go. It's just negative 4. Okay, so with that in mind, let's try this other one. So for this one, we go ahead and when you plug in you plug in a 1, you're going to get 1 minus 1 plus the natural log of 1. Well, that's just 0, so you get 0 on the top. On the bottom, we get 0. We get 1 minus 3 plus 2, which again gives us 0. So we're good. We've got 0 over 0, which means that we can use L'Hopital's rule. So we put a little h here. The limit as x approaches 1, and we're going to get negative 1 plus the derivative natural log of x is 1 over x. And on the bottom, we're going to get 3x squared minus 3. So we plug in 1, and we're going to get negative 1 plus 1 on the top, which is 0. The bottom, we get 0. And now this is where I'm going to say, go ahead and answer. What's better than a problem where you get to use L'Hopital's rule only once? And I know what you're thinking. A problem where you get to use L'Hopital's rule twice. That's right. And here we go. So we use L'Hopital's rule again, and we get the limit as x approaches 1. So at this point, remember with this one, 1 over x, it's easier to think of that as x to the negative 1. If you think of that as x to the negative 1, then when you take the derivative, you get negative x to the negative 2, or 1 over x squared, right? For the derivative of this, I'm just going to write it this way because I have to plug in a number. Then down here, we're just going to get the derivative 6x. And then this thing, we can just take the limit from here. Just plug in 1 at this point. Just take the limit, you're going to get negative 1 over 1, which is negative 1. You get a 6 on the bottom, and we just get negative 1/6. So this problem is probably your favorite so far because we used L'Hopital's rule twice. I'm going to ask you guys a question and see what you think the answer is. In the homework, there's this one problem. It's the one where you use L'Hopital's rule the most to get the answer. Guess what how many times you have to use L'Hopital's rule? To give up? 17 times. 17. No, not really. That would be pretty awesome, but no, I think the most is probably 3. So we don't have anything quite as awesome as 17 times. It's pretty rare to go past 2. Okay, so this brings us to the indeterminate products, which when you look at this indeterminate product, you can see already this is not going to work Remember, L'Hopital's rule is really picky. It's got to be 0 over 0 or infinity over infinity. This is not either of those. But we use this idea. If you have a function times another function, f times g, well, that's exactly the same as f divided by 1 over g, right? Because instead of dividing by 1 over g, couldn't you multiply by the reciprocal of 1 over g, which is g, which will get you here? And you could also do it this way. So f times g, we could think of it as two different ways. We could think of it as g divided by 1 over f, because again, that's the same as g times the reciprocal of 1 over f, which would be g times f, which is f times g, because multiplication is commutative, right? You can reverse these and get the same answer. So we use these two. Whenever you have 0 times infinity, one of these is going to get us where we need to go. And sometimes you just have to guess. Like sometimes you'll guess one and it doesn't work, so you have to try the other one. So that's what it's saying here. We use these facts up here, these two facts, to convert the given limit to one of these. We always need one of these. So to see how that works, let's try example 7. So when you look at example 7, and just looking at this thing, as x goes to infinity, we've got, let's see, we need to move this a little bit. Okay. So we've got x goes towards negative infinity, so x squared, when you square that huge negative number, you're going to get infinity. Then e to the negative infinity, that's going to be 0, right? So as x gets larger and larger negative, it's like e, think of like, let me think of it like this. If you have e to the negative infinity, isn't that like 1 over e to the positive infinity? So this denominator is going to be getting huge. So 1 over a huge number means this is going towards 0. So this is infinity times 0, which will not work for us. So we can either do x squared over e to the negative x, or e to the x over x to the negative 2, right? It's got to be one of them. So you basically just have to try one, and sometimes you're going to pick the wrong one, and you'll know because it will not look good when you start working with this, which I'll show you in a second. So let's say I'm going to put x squared on top, and then 1 over e to the x, right? Because I need to, like, this has to be equal. An easy mistake students make at first is they'll put like x squared on top, e to the x on the bottom. Well, that's not equal, right? This thing has to be exactly the same as this. So we can't just put it out however we want. It has to be the same. To make this equal, this is the same because this is x squared divided by 1 over e to the x, which is the same as x squared times the reciprocal, which is e to the x. So when we have it lined up like this, and then we go and evaluate, now if I plug in negative infinity, I get infinity on the top. On the bottom, I get 1 divided by e to the negative infinity, which is like, so think about what we've got. This is 1 divided by e to the negative infinity. Well, that's like 1 divided by 1 over e to the infinity. And 1 divided by 1 over e to the infinity is like e to the infinity, which is going towards infinity. So now the denominator is also going towards infinity. So when we write it like this, we have infinity times 0. But if we write it equivalently, like this is the same, now we have infinity over infinity. So now we can use L'Hopital's rule. So now we can say, okay, we've got one of those forms that we need. So we're going to use L'Hopital's rule. So I put a little h here. And we've got the limit as x approaches negative infinity. And we get 2x. And on the bottom, well, this one, 1 over e to the x, if I'm going to take the derivative, I would probably write it like this, right? When it comes to taking the derivative, because these are the same, If I take the derivative of this, I need the quotient rule. If I take the derivative of this, it's a little easier because the derivative of e to anything at all is itself, e to the same thing. But then since this is not plain old x, the chain rule comes in and says take the derivative of negative x, which is -1. So down here, I'm going to get minus e to the minus x. So if you're not sure about that, just pause this and think about it. We're taking the derivative of this, but I'm going to first write it like this because it's easier. The derivative of e to the x is just e to the x, but the derivative of e to the negative x is e to the negative x times the derivative of negative x, which is -1. So that's how we get the negative here. So then if I try to take the limit and I plug this in the numerator, I'm going to get a negative infinity. In the denominator, well, think about what we've got. We've got e to the minus infinity. That's e to the infinity, right? E to the minus infinity is e to the infinity. Then we've got this negative out front, so we end up with a negative infinity on the bottom also, which is okay because that means we can use L'Hopital's rule. So we have, let's see, no, that's not what we wanted. We have the limit as x approaches negative infinity, and here we're going to have the derivative of 2x is 2. Remember what we're doing, we're taking the derivatives of these individually. You don't want to do the quotient rule here. It ends up, if you're doing L'Hopital's rule and it's getting really terrible, something's not right. L'Hopital's rule makes life easy. So individually, the derivative of x squared is 2x, derivative of 2x is 2. And same thing with this, we take the derivative of these individually. So the derivative of e to the negative x, we already know that's minus e to the negative x, and you have a minus here already. So this ends up being positive e to the minus x. And now we can take the limit of this, and this is going towards negative infinity, so we have e to the minus infinity. That's e to the infinity. So that's growing without bounds. So we're going to get 2 divided by infinity, which is just equal to 0. So that one is 0. So what I had mentioned earlier was, we kind of right here just sort of guessed to put x squared on top. And there's really only 2 ways we can go. One of these is going on top, one's going on bottom. So here's what would happen if you do the other way. So here's, I'll just say be careful. If you happen to pick the wrong way, and sometimes you will, when we do this, we'll get the limit as x approaches negative infinity. And let's say we put e to the x on top. And x to the, if we put x on the bottom, it can't just be x squared, it's got to be 1 over x squared, or x to the -2. So the big difference between this one and this one is this. When I take the derivative of x squared, I get 2x, and then 2, and then 0. This one eventually will go away, or this one's not. This is e to the x, it's not going away. Well, down here, e to the x is not going away. Every time I use L'Hopital's rule, I'm still going to get e to the x. But this time, this isn't going away either, because the derivative here is going to be -2x to the -3. And then the derivative there is going to be, well, so if we have, like, let's just to see what's going to happen. Just looking at this derivative is e to the x forever. The derivative of this is going to be -2x to the -3. Then the derivative of that's going to be 6x to the -4. But neither of these are ever going to go away. So if you get into a loop like that where you can't get out, that just means flip these around and try it again. And this one, you can see with the x squared, is going to eventually go away. So that can happen sometimes. But you'll know when it does because this thing is just getting worse all the time. So another thing that we will see is what's called indeterminate differences. And this is of the type infinity minus infinity. So when we get one of these, you want to try to convert differences into a quotient or a product. And basically what we want to do is try combining the terms or factoring out a common factor. So basically it's going to be combining the terms or factoring. So an example look at here, example 8. We've got the limit as x approaches 0 of cosecant x minus cotangent of x. Now these two functions are not studied all that often, but you probably have seen them in either pre-calculus or trigonometry. But if you're familiar with them, you could say, well, this is going to be infinity minus infinity. But I'm going to guess that most of us are not all that familiar with this one, with either of these. So what we can do instead is just do what we typically do when we run into these and just rewrite them in terms of sines and cosines. So this is the limit as x approaches 0. Cosecant is 1 over sine of x. And of course, cotangent is cosine of x over sine of x. So if you were familiar with these and you looked at the graph and you saw, well, it's infinity minus infinity, well, it doesn't look like there's much to really factor here. But once we write them like this, we could easily combine these. We could easily combine these now because we've got a common denominator. So for that common denominator, we could say, well, that's the limit as x approaches 0. And that's just 1 minus cosine of x over sine of x. And now these functions we should be very familiar with around 0. So if we were to plug in a 0 right here, we would get 1 minus cosine of 0 is 1 minus 1, which is 0. And of course, sine of 0 is 0, so we get 0 over 0. So at this point, we're okay. So we can just go ahead and use L'Hopital's rule. And that would give us a limit as x approaches 0. Remember, when you use L'Hopital's rule, we typically just put an h here, just so everybody understands what we're doing here. Why we're saying that this limit is the same as this limit when these functions change. The h lets us know, lets any reader know that we're using L'Hopital's rule. So the limit of 1 minus cosine of x, well, the derivative of cosine is negative sine, but that's a negative cosine. So the derivative of 1 minus cosine is just going to be sine of x. Derivative of sine is cosine of x. And at this point, we can just take the limit because as we plug in a 0 here, we get sine of 0, which is 0. So it could be we're going to get another indeterminate form, but we don't, because when you plug a 0 here, we get cosine of 0, which is 1. So we get 0 over 1, which is just 0. So when you see these indeterminate differences, you see this infinity minus infinity. When you see these, look for things to factor. Usually you can factor something out, or if that doesn't work, look for some way to combine the expressions. And then the ones that are the trickiest, ones that give us the most trouble because they are kind of a step up in the work, are these three types here. When powers are involved, like in a lot of cases, we need to use logarithms, and it's no difference here. Each of these three indeterminate forms can be handled the same way, but they are a little tricky. And again, we have this weird formatting here, but we've got this this limit here, the limit as x approaches a of f of x raised to the g of x. And these three indeterminate forms can come up with this. We can come up with any of these three. And they're all a little bit of a handful. So there are different ways to do this. I'm going to show it one way, and I don't think my way is a great way. But the problem is I haven't seen a great way yet. So Stewart uses a little bit different way in the book, and maybe you guys learn some other way. Every way I've ever seen this explained is kind of a handful. So I use kind of a step-by-step approach. if you learned it a different way, you might like your way better, but I'm going to show you a way that always works, but honestly, there's not a way that I've seen that is really good for these, really straightforward and simple, but I'll show you the way that I always teach these. So first, if we look at this one, we can see that the form is 0 to the 0. So first, when we look at this one, we can see that this form is 0 raised to the 0. So that's the form. It's one of those three indeterminate powers. So here's the process that I usually go through on these, and it works on all of these the same way. I do 4 steps. So the first thing I do is I let y equal whatever that expression is, x to the x in this case. I always just let y equal that. And then we're going to do pretty much what we always do when we have this situation. We're going to take the natural log of each side. So step 2, I now take the natural log of each side of this equation here. So I have the natural log of y equals the natural log of x to the x. And we do that exactly what you would think, because then we can bring this down here. We use that rule of logarithms that we've been using all semester. And we say, so then the natural log of y equals x times the natural log of x. So step 3, and there's 4 steps. Step 3 is the one where all the work is done. And then step 4, we kind of just summarize everything to get our answer. So step 3, what we do is we use this limit. We take this limit just like it says here. So we go limit as x approaches 0 from the right. But what we do is, instead of doing the limit of this, which was what we want, instead we take the limit of natural log of y. So we have the limit of natural log of y, and then we know that the natural log of y is just this. So now I'm going to say this equals the limit as x approaches 0 from the right of x times the natural log of x. And I know it looks like we're kind of writing some redundancies here, some things we don't need, but it'll make sense when we get to step 4 and we sort of put all the pieces together. So when you look at this one, as x approaches 0 from the right, we're going to get the form we've got is 0 times, and to see what we've got, just think of the natural log of x function. So natural log goes like this, right? So as x approaches 0 from the right, the natural log is approaching negative infinity. So this is really 0 times negative infinity. So it's 0 times infinity. So what we have to do is put one of these on top, one on bottom. And remember, we put one on bottom, we have to go 1 over that. So again, it's a 50-50 thing. But if we write it like this, if we go the limit as x approaches 0 from the right, and if we go natural log of x divided by 1 over x, and you can see this is the same as this, right? Because natural log of x divided by 1 over x is like natural log of x times the reciprocal of 1 over x, which gets us right here. But now, if you look at what we've got here, now as x approaches 0, the numerator is going to go towards negative infinity. And the denominator, as x approaches 0, this gets really small, and this is constant at 1. As this gets smaller and smaller and smaller, we can make this as large as we want. And it's approaching 0 from the right, so they're all positive values. So we get an infinity on the bottom. And at this point, we're all set. We can use L'Hopital's rule. So we take the L'Hopital's rule here. So we get the limit as x approaches 0 from the right. And the derivative of the numerator, the derivative of natural log of x is 1 over x. The derivative of the denominator is negative 1 over x squared. right? Because this thing is really x to the negative 1, x to the negative 1, right? So you have x to the negative 1, you take the derivative of that, get minus x to the minus 2, which is equal to negative 1 over x squared. So if we clean this up a little, so this is 1 over x divided by negative 1 over x squared, which is the same as 1 over x times the reciprocal of this, which is just negative x squared. So that's just going to give us the limit as x approaches 0 from the right of just negative x, right? This thing is just negative x. And when we take the limit of that, you just get 0. So all of that work, the limit is just 0. And this is x approaches 0 from the right. So step 4 is where we kind of put the pieces together. Again, it's kind of a lot of work. All of these are kind of a lot of work. But we'll do one more like this with the 4 steps. And you'll see once you do a couple of them, they're not really bad, but they're a little bit of work. So finally for step 4, we are going to answer the question we originally were asked. The limit as x approaches 0 from the right of x to the x. Well, so to do this, we could say this is the same as the limit as x approaches 0 from the right of y. Because up here we said we're going to let y equal x to the x. The reason we're going to do this is because earlier in the semester, we showed, and we did a real quick proof, that y is the same as e to the natural log of y. So this came up earlier, and we had to show that we showed that x is the same as e to the natural log of x, and I had an example like if you plug in e to the natural log of 7, you should get a 7. And we proved that earlier in the notes. It's a real short proof. And we're going to use it again here. So there are reasons we do these things. So it seems like we're putting a lot of extra work in here, but it's just to make the logic work. So we want to find the answer to this limit, the limit of this. Well, we know that's the same as the limit of this, and that's the same as the limit of this. And once we get here, if you look what we did here, we found the limit as x approaches 0 from the right of natural log of y, and that's pretty much where we're at here. So there's a step I'm going to put in here, but it's totally optional. So all of this in red is optional, but this is equal to e to the limit as x approaches 0 from the right of the natural log of y. This whole thing is optional. You don't have to put this step. I'm putting it in here so you know why this works. And the reason this works, this is from Theorem 8. And this is on page 120. And the theorem actually, it's a nice theorem. It says that the limit as x approaches a of f of g of x is equal to f of the limit as x approaches a of g of x. And it basically says we can do that as long as these functions are continuous. So we can, if we are going to take the limit here, the limit of e to the natural log of y is the same as e to the limit of the natural log of y. But normally we don't actually show this step. So I wanted to show it once so you know why we're doing this. But normally what we'll do is we'll go right from here. And we already, look what we did up here. So we already showed this up here. We found this. We found that this is just 0. So what we're going to do here is just skip this and just go right to this and say that this is equal to e to the 0, right? Because we found the limit as x approaches 0 from the right of natural log of y. We found that the limit of this thing is 0, so we get e to the 0, which is just 1. So after all of that work, the answer to the original question, which was in the form of 0 raised to the 0, the answer is just 1. And this is a 4-step process we can go through to find the answer, and it will work on these every time. Kind of a lot, I know. But like I said, there are different methods for this, and they're all kind of a lot. So here is one last example. And I want to do 2 of these kind of just so you see that we can do it the same way. They all work the same. And it'll work every time when we have these. So looking at this one, look at the type of problem we've got here. So we're going to take the limit as x approaches 0 from the right. And when we plug in 0 here, we know we're going to get 1 plus 0. So we have 1. So we have a base of 1. And then if you plug in a 0 here, you get cotangent of 0. Well, cotangent, remember cotangent is just cosine of x over sine of x. So if we're going towards 0, we are going to get 1, or cosine of 0 is 1, sine of 0 is 0, so we're going to get, this is going to be heading towards infinity. So the form that we have right here is 1 to the infinity. Again, it's one of those 3 indeterminate powers, and we can handle all these exactly the same way. So here's where you'll start to see the consistency. So step 1, we just let y equal that expression that we've got, which is 1 plus sine of 4x raised to the cotangent of x. Step 2, you remember what we did for step 2? Natural log, right? We take the natural log of each side. Natural log of y equals the natural log of this thing. And the whole reason we do that is because then we can bring this down. So that's what we do next. We say that the natural log of y is equal to cotangent of x times the natural log of 1 plus sine of 4x. So that's exactly what we did last time, and this will work on every one of these indeterminate powers. So then we go to step 3. And again, step 3, this is where all the work really is involved. So step 3, we take the limit as x approaches 0 from the right of this natural log of y. Right, so we take the limit of this, which we know is equal to the limit of this, so we just write that out. That is equal to the limit as x approaches 0 from the right of cotangent of x times the natural log of 1 plus sine of 4x. So when we look at this one, if we take the limit here, as x approaches 0 cotangent, because it's cosine over sine, that's going to go towards infinity. And then the natural log, think what we've got here. We've got as x approaches 0, this goes to 0, so we have the natural log of 1, which is really, it's not quite 1, it's 1 plus a bit above 1. But as this approaches 0, the natural log of this is approaching the natural log of 1, which is 0. So this is going to be infinity times 0. So just like before, we had to put one of these on top of the other one to make this work. So we've got the limit as x approaches 0 from the right. And this one takes a little bit of well, I mean, it's one. There's 2 ways to do it. You pick one. And this one is definitely going to be the easy way to go, because if I put this one on top, then I have to put the reciprocal of this on the bottom. 1 over cotangent. What is 1 over cotangent? 1 over cotangent is tangent, right? The reciprocal. So I can just put tangent of x down here. If we did that the other way, I would have had to put cotangent up here, and I'd put the reciprocal of this, which would be 1 over this whole thing down here, which would just really get to be messy when we took the first derivative. Where if I do it this way, I put this on top, and the reciprocal of this on the bottom, because it's 1 over cotangent. 1 over cotangent, which is just tangent. But the nice thing about this is if we take the limit now, as x approaches 0, we're going to get the natural log of 1, which is 0, and tangent of 0, which is also 0, because remember, tangent is sine over cosine. So that's going to be 0 over 1, which is 0. So at this point, we have got 0 over 0, so we're ready to go. We can use L'Hopital's rule here. So we say this is equal to, put a little h for L'Hopital's rule. The limit is x approaches 0 from the right. We take the derivative of the top. Now it looks like it could be a little messy because it is the natural log. So you take the derivative of the natural log, it's 1 over the argument, so it's going to be 1 over this times the derivative of the argument by the chain rule. So that is going to be, let's see, take 1 over the argument, which is 1 plus sine of 4x, times by the chain rule the derivative of the argument. The derivative of sine of 4x is cosine of 4x times 4, right? We're taking the derivative of the inside. The derivative of sine of 4x is cosine of 4x. And it's not plain old x. The derivative of 4x is 4, so we get cosine of 4x times 4. And then on the bottom, the derivative of tangent is secant squared. And now, if we go to take the limit, let's see what happens if we take the limit. Well, sine is x approaches 0. This is going to be sine of 0, which is 0. So you get 1 over 1. So this is just 1. Cosine of 4 times 0 is cosine of 0. That's also 1. And this is just 4. So on the top, we get 4. So on the top, we get 4. And the bottom, well, think about this. Secant squared is 1 over cosine squared. And cosine of 0 is 1. So this is going to end up being 4 over 1, which is just 4. So we go to the last step here. Step 4, we put all this together. Step 4, we say the limit is x approaches 0 from the right, the thing that we originally wanted, which is 1 plus, move this up a little bit here, 1 plus sine of 4x to the cotangent of x. That's equal to the limit is x approaches 0 from the right of y, right? Because remember earlier we said let y, our first step, let y equal this. The reason to do that is because now we can go to this identity. The limit is x approaches 0 from the right of e to the natural log of y. Remember, because y is always the same as e to the natural log of y, no matter what you plug in here. 5, e to the natural log of 5 is just 5. So this is the identity here. And then we've already taken the limit of, we've taken the limit as x approaches 0 from the right of natural log of y. That was right here, and we got 4. So because of that, this is the step we're going to skip. We're going to skip this step about theorem 8. We just get e to the 4. And that's our final answer. So go ahead, try this section out. L'Hopital's rule will make life much easier with limits, but maybe a little bit harder when it comes to these indeterminate powers. But they take a little practice. Indeterminate powers can all be solved with these 4 steps. So try out this section homework and let me know if you have any questions.